Here's what we're going to cover. We're going to talk about why we built this and what it's for. We're going to show you some apps that have built with Electric. We're going to spend a lot of time talking about how it works on the first tutorial. We'll analyze every line of code to have a good understanding of what's happening. I will show you many demos. We will talk about strong composition, which is a goal. And we'll talk about what that means and why it's important. We'll talk about FAQ, how to deploy project maturity, what the issues are if you try it. And I am monitoring the chat, so put your questions in the chat and I will see them. Okay. So let's start with why we built this. It's for enterprise apps, single page applications. So as an example of an enterprise app, this is an app that I built in 2013, 2014. This is actually the Scala backend app I was talking about. And we've all made many CRUD apps like this in our career, right? Lots of forms, lots of tables. It's pretty complex. There's complex business rules, validation, etc. So we're trying to solve this problem. Here's some apps that we've made with Electric. This is a partner app. So what a partner app is like, it's not an app that you give to consumers. It's an app that you put in front of your partners. It's like an internal operations app. This one's for a Series A SaaS business. This is going live in a couple weeks. Here is an internal production support app for a Series B startup. They use Datomic. Ignore the DSL on the right. We'll talk about that later. But on the left, they just have a SaaS business where they get a lot of email support and they have to like execute these business transactions against their database, just a CRUD app. So we built this with Hyperfiddle and the thing that came before Electric. Here's the next version of that same internal support app. This one is built with Electric. It's a bit of an experiment. It's like, how can we converge these internal production apps to look more like a spreadsheet? Because for internal applications, we don't care so much what the styling is or what it looks like. We care about like a strong user experience. We care about having high quality widgets, but we don't care about like the exact styles. And if you can constrain your app to have that structure, it brings us to this idea of what if we had an Eden-based DSL that could encode serious operational CRUD apps like this. So the more structure and spreadsheet-like aspects we can converge on. What if we could like write down the semantics as a DSL and then give that as a way for people to build applications? And if you had such a DSL, what if you made it so that you could interact with the DSL and type the DSL live and have a CRUD app happen? So that's what's happening here. This video is a proof of concept. It's about a year and a half old maybe, and we are typing a CRUD DSL, and you do get a real full stack CRUD app live as you type. So this is what we're trying to do. Data browsers. An interesting thing about data browsers like Rebel is they're read-only for the most part. So what's the difference between a data browser and a CRUD app? Why can't we use Rebel or things like Rebel as actual composable application primitives that you can use to administer a SaaS business? What is Rebel missing that a SaaS business needs? And then here are some apps in the wild. You can see a data browser. You can see there's a spreadsheet. There's a Clojure spreadsheet. Use S expressions as a formula language. Here's another report for that spreadsheet. Here's a medical app. We have some real-time games. We have a open map extension. We have a YouTube player. These apps were made, I think, in the first 2 or 3 months after we released. So there's even more now. So that's what Electric is for. Here's what we're not for. We're not for websites. We'll probably never be for websites. We're focused on rich, dynamic things like a word processor or Webflow or Google Sheets, right? Productivity tools, the hard stuff. If you want to build things with server-side rendering, React.js has an incredibly good stack for this at this point, very mature, right? Tons of investment from many companies have gone into making that good. So while, yes, perhaps we do this someday, in the next 2 years, we are not focused here. Okay. So as a problem statement, if you take something like Facebook, it's clear to everyone that like there's a unit of composition happening here. But this unit of composition includes state, network, interaction, and rendering. And React.js was great at giving us a composable rendering model, but it doesn't include like the user interactions. That is done through callback change handlers. It doesn't include the network. It doesn't include the state. And we will talk about React Server Components. They do have an attempt at managing the network now, and we'll talk about its limitations. So how do we encode this more semantically? Really, the question we're asking is, if we want to make a CRUD app, what we actually want to do is compose the view directly with the DOM, right? So you end up with a really cute expression here where it's like very clear what the data flow is. You start with the database, you query the database, and then you render it to the DOM. But that's not how it is today. We have ORMs, like you start having to add framework code in here. You have to start like registering query subscriptions. You break the composition, right? This is like the true essence of the data flow. You can even draw on the whiteboard like as a graph the data flow through this, and then we destroy it when we have to add in a heavy framework to make this actually operational and meet the operational aspects that a real application needs. And to go further, real applications have a more complex topology than just this. So this t-shirt orders demo is the kind of the minimum viable application that demonstrates a complex client-server interaction. So what you have is a query. Your query is a function, and then you need to render that query to a table. And the table contains like columns as a form, but it also contains select options. And the value in the select option comes from the query. But not only that, but the options can depend on what the user types. So the user types into a string input on the select on the browser, and it needs to end up on the server, right? And rerun a different query. And then that could even be more complex because you have a select option that has a sideways dependency on the record to the left of it. So you have a database that has a gender record, and then you need the gender record to get the shirt sizes so that you see the men's shirt sizes only if you have a man record. And again, like you look at this and it's very clear, like and elegant and concise what the data flow should be, but it won't work because this needs to be on the server, this needs to be on the client, this needs to be on the server, this needs to be on the client, right? And you have a very interleaved data flow. And you can't even batch it properly because like when you rerun the shirt sizes query because they typed, like you need to know the gender too. So if you just send up the string to rerun the query, it's not enough. You have to send up the gender also. All right, question is the backend rendering or the front end rendering? In Electric, the front end is doing the rendering, and we'll demonstrate that in a second. This actually isn't Electric code. This is meant to be like pseudocode to demonstrate the problem. We have this interwoven dependency flow or data flow that needs to cross back and forth between the client and server in a very rich way. And the theme I want to talk about here is this is essential. If you look at this, there is no line in this that can be removed without losing a necessary feature. So I propose to you that this is the essence of the problem of a CRUD app. And starting from here, we start to break this essence by adding in framework stuff in order to manage and orchestrate the state and the side effects. So as a goal, if we want to reduce accidental complexity as Clojure programmers, this is true north. This is the target. How can we make our code look like this? And if you could make your code look like this, like you can build anything because you have Lambda. We know that Lambda can build an operating system. Lambda can build Emacs, right? Lambda can build a web browser. So how can we make our CRUD apps work like Lambda in the presence of network? All right. So this is important because if you solve this, not only does it make it possible to express more fluent tools, but it also makes it accessible. Because if you look at code like this, like anyone can understand this. Someone with like 2 weeks of Clojure experience can write this. What they can't do is Django warm, Django model, right? It immediately like destroys the clean essence of this and adds all this cruft. So if we can solve this problem and make our code look like this, it would make programming dramatically more accessible. Okay, why now? The cloud is 10 milliseconds away. This matters because it gives you more tolerances with respect to your I/O. You can consider like a real-time or streaming abstraction, and also the technology is mature as well. And then the maturation of functional programming matters. When I started out as a Scala programmer 10 years ago, like we were all exploring category theory and monads for the first time, and we weren't very good at it. And it kind of took the industry about 10 years to figure out like what this is even good for, right? It's not about HTTP servers, but monads. It's about what does a functional effects system get you, right? It gets you process supervision, it gets you cancellation, it gets you glitch-free rendering, and we'll talk about that later. Also, functional programming is mainstream now. Something like this would be like mocked or ignored 10 years ago, or written off as impossible. But like now there's like a clear adoption path. Like people understand and want something like this. And then of course, Clojure. The value prop of Clojure will be, I think, pretty clear once we talk more about how this works. Okay, so the final thing before we jump into the code is I want you to think about, if this is how we want to define applications, this is function composition, but it's not like function composition in Clojure, because Clojure can't do this. Clojure can't compose a backend function with a front-end function. And it's not ClojureScript either, because ClojureScript can't compose front-end with backend. So it makes you ask, what actually is a function anyway? And this comes from like a study of category theory. Like the word category in category theory is about what it means to compose. This is the comp operator in Haskell, and it abstracts the idea of, like, given a function from A to B and a function from B to C, what does it mean to compose those two functions? And if you generalize and abstract this structure that we call composition, you might find, or you do find, that it works for more than just like vanilla functions. It works for asynchronous functions. It works for stream functions. It works with reactive functions. So how could we look at this and, without changing the syntax at all, use a macro to change what a function means and yet maintain the composition model? So that's what electric Clojure is about. I'm going to stop here for any questions and check the pulse on how we're doing before I jump into the next thing. I'll wait for about 30 seconds. All right, I'm going to move forward. Okay, problem statement. Okay. Oh, question. Electric has a nice use of creating HTML. To use different existing custom web component HTML element is a way to add these. Yeah, Electric DOM, which we'll talk about in a moment, is only 300 lines of code because all the heavy lifting is done by Electric itself. So we've actually seen someone in, he said 30 to 40 hours, he made a 3JS 3D renderer bindings for Electric. So you absolutely can integrate external things. If you want to use reagent, or if you want to integrate a React component, we have examples for how to do that. I hope that answers your question. Okay. Now let's talk about the hello world. So what's happening here? Here we have two clocks, a clock on the server and a clock on the client, and they are streaming. So here is the server clock, and we've marked it as on the server. And we see that not only is the server streaming to the client, it's also it's streaming directly into the DOM. It's rendering directly. We also see we have these eClient marking and eServer marking. So we're not like writing code about like promises or IO manually. We're just indicating as like a static marker, as syntax. We're saying, I want this clock to be on the server, and I want this expression to be on the client, and I want this expression to be on the client. And what Electric will do is it will analyze the syntax using a macro. This macro essentially implements an actual Clojure and ClojureScript analyzer, and it compiles this down into a Clojure program and a ClojureScript program that coordinate. Anything that's in an eClient block is treated as ClojureScript, and anything in an eServer block is treated as Clojure. Now, to pause for a second, if I just gave you this as pseudocode, forget that it runs. I gave this as pseudocode. it contains like the essence of the problem. Given this as if like a manager gave this to you, you could go implement a REST API GraphQL for this. It's clear what the requirements are. And the compiler, the electric compiler, has the same knowledge that you have in terms of this. So it is theoretically possible to take this and then transform this into a client-server system. The question is how. And what we do is we analyze this and compile it into a DAG. Now, DAG is a directed acyclic graph. It actually has cycles, but this program does not. So this program is a DAG. And what we mean is when this reactive clock fires, what happens next is we know that the C variable needs to stream, needs to update. And the C variable has an edge in the DAG to this place that references the C variable. So this is an edge in the graph. And then when this changes, it means the DOM text needs to update. So that's an edge in the graph. And if the C updates, also it means the minus updates. And when the minus updates, then the text updates. So you can see the data flow is implied by this AST. And there's actually an isomorphism here. You can take any Lisp AST and you can think of it as a graph. And if you think about it, you knew this already, because if you use like a Java IDE, it gives you a call graph. So that's all this is doing, is it's analyzing this into a graph, and it performs coloring to know which parts of the graph are on the client and the server, and it shakes it out, and then it compiles that in a separate pass down to Clojure and ClojureScript programs. Okay, let's talk a little bit about C and S. C can be thought of as both a value, it's the current time, or it can also be thought of as a flow of values, the reactive time. Both of those worldviews are true. So when you write your code, you say, okay, C is the current time, the server will stream it, and then when we render it here, we're rendering with the current time. But you can also think of it as a stream of time. So to understand what the compiler is doing, think of it as streaming lexical scope. Like literally let is compiling down to a stream, and this clock will be bound to C, which is a stream on the client because it exists in a client block. So electric is about streaming lexical scope. Can you zoom on the text? Is it too small here? I also now want to compare to like the approach that you might see in a pure function, a typed functional programming community. And that's called the monadic style versus the direct style. How do I make this bigger? So if you use typed functional programming, monads have this flat map operation. So you might say, okay, I have an asynchronous type, a future or a stream or a promise, and I need to do callback chaining like promise chaining or flat map chaining. That's what monads give you. And you have to like explicitly write out like the chain operation, the flat map operation in order to combine them. And when you do it this way, like the types are explicit in this Scala program, like the type is visible to the application programmer. Flat map is on the monad type class. So this function read of type A returns a ZIO type, which is a monadic type. And Scala comes with ways to like make this better, because obviously that doesn't scale. Has for comprehensions, which is, you know, basically a macro that compiles this to monadic code. But the for comprehension syntax has problems also. It's very difficult to put an if statement in it, for example. So this led people to come and understand what is called the direct style. And the direct style is when you just write the code that you wanted to write in the first place in Scala, and you essentially use macros to compile this code into the monadic style. And that is essentially what Electric Clojure is doing. We let you write your Clojure program in the direct style of Clojure, and then we compile it into some other reactive computation. Okay, is that nested eClient needed? No, this is not needed. I put it here only for learning purposes. Great catch. All right, any danger in the ClojureScript and Clojure data types being based on their host environment? Yes. when you stream this here, we use Transit to serialize and send it over a WebSocket. So Transit is a Clojure serialization library. It handles like out of the box Clojure data types, and you can extend it with custom data types. You need to have a Transit serializer, and if you have a Transit serializer installed for it, it just works. To see being a value and a flow at the same time create issues that you might need to consider as a dev. It depends on what you're trying to do and what layer of abstraction you're trying to think at. We originally had named this project not electric but photon because it's a reference to quantum mechanics, where a photon is both a wave and a particle, and you need to depending on what you're doing, you can think of it either way or both ways. You can't get a full understanding of your program without both of those worldviews, and we think that's true here too. It's important to be able to forget about the reactive types and just think about values, and it lets you write like direct, straightforward code like this. But sometimes it's also important to think about it as a flow or as a reactive stream, because what if you're making like a complex component that like integrates with a third-party JavaScript library which has all these callback interfaces, and you need to like drop down and bridge them to electric. So you do need both, and it's our hope to be able to make it so that you can use the simpler worldview for almost everything, the way we think about light as a particle, except when it really comes down to it, you have the ability to drop down and think about this as a reactive type, which it really is. Okay. All right, DOM text. I want to talk about what this is doing. First of all, this is kind of ugly, right? It's not hiccup. And why do we have to write this? What even is this? And now if you think about it, if you've written low-level DOM code before, like underneath React.js, you just manipulate the raw DOM. You can't just put a string into a div. You have to create a text element, and then you put the string in the text element. So what this is doing is it mimics the actual structure of the DOM. This is a point effect. When you first run this component, what it does is it will allocate a text node by calling javascript.document.create text node. And then it will attach the text node to the parent div by calling append child. And then it will say text node.setText this and then this. It combines them or something. I forget what it does. So what's interesting is this is like the true structure. It shows you like the true effects that are happening. And also, because it's just a simple point effect, when C changes, this point effect will rerun. Think of it as a println. It just runs again, updating and overwriting in exactly the right place to DOM. So you end up having a very simple to reason about execution model where you don't have like React.js has this differ and this reconciler, and like you have to understand their special edge cases and like how do you know like what's going to evaluate and what's not. It requires experience. The rules are very simple here. If C updates, rerun the function. If any argument updates, rerun the function, and that's how it works in every S expression. If S updates, this one will update, this one will not. And in this one, if either C updates or S updates or both, it will rerun the subtraction. And then because this depends on the subtraction, it'll rerun the point effect. So you have a very simple, effectful DOM layer, and this effectful DOM layer is 300 lines of code currently. Electric DOM is 317 lines, including white space and tests, something like that. And that's because all the heavy lifting is being done by Electric. So we've just generalized rendering. Okay, any questions about what this program is doing before I move on to the next one? Let's review. We have streaming next scope. Okay, does DOM div depend on the DOM text? Will it rerun as well? Yes, I believe it will, and it will work skip because there's a reference. I haven't introduced enough about Electric to actually answer this question properly. The answer is it will not blast the div. It will rerun the effects that are necessary based on the DAG, and the computation will stabilize and stop because it'll have like this DOM text element returns the DOM text node, and since it's the same DOM text node as it was before, the div function actually got an argument that is equal to the last time it was called because it's the reference to the text element, and it will stabilize and stop. So the computation will automatically be efficient due to these work skipping semantics. Let me talk a little bit more work skipping actually. If you think about this subtraction, first we are reusing, if C changes and S didn't change, it will reuse a cached previous value of S. So there is some form of caching happening here, and that caching is happening actually at every S expression. The arguments are cached. I mean, you could think of reactive programming as a time-space trade-off. You pay these caches everywhere, and in return for that, you get to reuse past results without computing it. So that's fundamentally the optimization that reactive programming gets you, is it lets you compute faster, even in real time. You can render in real time at the cost of the expense of memory. Okay, how do you solve pushback from the client to the server? Server is fast, rendering connection slow, etc. So this is about back pressure. This compiler will compile the DAG down to reactive code using the missionary reactive programming library that supports Clojure and ClojureScript. And what missionary is essentially a set of concurrency combinators that let you control back pressure and let you control caching and let you control like the exact allocation boundary of each cache and in control like which pipelines are eager and which pipelines are lazy. In this case, if C and S are happening very quickly, you don't actually care. Like, imagine the client is just too slow. Like it's just like your battery's dying on your phone and the client can't keep up. You don't necessarily have to render all the intermediate frames. You just want to render the most recent frame. So think of it like a 3D video game. If your video card is too slow, you just drop frames. Like a frame that happened 3 seconds ago is no longer important. You don't need to compute it. You just forget about it. And that's a form of back pressure. And the missionary reactive programming library is a language of combinators for expressing back pressure in very rich ways. So that's essentially how we achieve this. Okay. Imagine someone has written 2 clocks. How would they go on to test it as an application? Let me hold the question about testing for later. I want to introduce more ideas first. Okay. Streaming lexical scope. Programs are DAGs. They're actually directed graphs. When we say DAG, it's kind of like a marketing term because people know what DAGs are. Hacker News knows what DAGs are. They're very comfortable. It's like we kind of say it on accident. It's really a directed cyclic graph or a digraph. But you know, who's paying attention? Note that it's declarative. It's declarative with respect to the data flow, meaning that you don't have to like write out that like there's a connection between this minus computation and this clock. You can just trace the data flow in this that's written in this declarative style to figure out what the edges are in the dependency graph. So that's important. Compiler is graph analysis, reactivity compiler. We use macros. There's an actual ClojureScript analyzer inside these macros. And one thing people ask is like, well, this is all really heavy, right? Like, it's this heavy compiler. It's actually shockingly simple. Once you frame the problem correctly and you realize what we have is a graph, we have a reactive client, reactive server, which are both just like subcomponents of the same graph. It almost falls out for free. So electric is 3,500 lines of code. Electric DOM is 300 lines of code. Missionary, the functional effects system, is 2,000 lines of code. And this is a parallel, this is as a Java implementation, which is separate from the ClojureScript implementation because it's fast. It's written in the direct Java primitives. What if dropping frames is not acceptable? In web development, it is because it's an animation. You just always want latest. There are other types of programs where you don't always want latest. An example where you don't always want latest is you have like a stream of database transactions. If you skip a database transaction, that's bad. You've corrupted state. that's awful. Whereas if you skip a frame, it's meaningless. So missionary has ways to express both eager, discrete computations which cannot be skipped, and also lazy, continuous computations which can be skipped. And electric Clojure compiles down to the type that is lazy. There are parts of a UI where you handle user interaction, which is events from the DOM, and like if the user hits enter, that's discrete. You can't skip that event. You would use missionary for that piece of code, not electric. So we're actually building a set of UI primitives that abstract over things like this, and they are implemented internally, either using electric or using missionary discrete flows for anything that cannot be skipped, work that cannot be skipped. Okay. What is a functional effects system? So missionary provides essentially these features or capabilities. Glitch-free propagation. This means that it will render optimally. It will choose, when C updates, it will choose an evaluation order in terms of like which functions to compute and in which order to compute them. That does not allow you to have like a computation of something that's inconsistent. It ensures consistency of your views as you propagate. So you never see like a subtraction on the wrong values that was then followed up by a subtraction on the right values. You'll never see that. That's called a glitch. Cancellation means, imagine you have like a JavaScript application and you have using promises, and you have a long running query on the server that you used a promise to create, and the query took too long and the user has like looked away or navigated away. That query is still running on the server, and there's no way to just to use a promise to cancel it and indicate to the server, hey, you don't want that anymore. That's what cancellation is, and missionary provides that capability. So missionary reactive types, as well as it has an async one-off task type. They support cancellation, which is important. Once you have cancellation, it gives you resource lifecycle. So imagine this div right here. At some point in time, we are going to look away from this application and navigate to some other application like I just did, okay? What missionary will do is it will cancel the render process, which propagates in reverse through the DAG a cleanup signal. So this DOM div is actually like React use effect. It has a mount and an unmount callback inside of it, and it knows how to attach itself to the DOM, and it knows how to remove itself from the DOM. And missionary is the thing that guarantees to you that the cleanup callbacks will absolutely be called, and they will be called in exactly the reverse order, and therefore you can use this for resource management, such as a database connection or heavy things like the DOM. Composability. Missionary has an emphasis on functional programming and referential transparency because it allows you to compose it up into a massively complex fabric of effects like this managing the DOM. How can you have an effectful DOM that has thousands of DOM nodes, that's thousands of effects that you need to orchestrate in such a rich and interwoven way? Composability and referential transparency of your effects is how you do that. So that's what functional effect systems are, and that's why they're so important to electric. If the generated front end and back end code are separate, how do you correctly repoint the front end to the correct back end URL? Okay, so this is a Clojure CLJC namespace. So from the programmer's perspective, the front end and the back end are defined in the same file. The build will compile it, yes, to a JavaScript artifact and to a jar file for prod or something. And they are keyed to each other. They are like a sports team. They have like, they use this AST as a playbook so that like when you throw the ball, in American football, the receiver doesn't have to ask for the ball from the quarterback. The quarterback just throws the ball, and he doesn't throw it to where the receiver is. He throws it to where the receiver is going to be, so they can anticipate each other's needs and act with a very small amount of chatter. So that's how they coordinate. They absolutely have to stay in sync. So for example, when we deploy, we know the backend and front end both know what version they were deployed on, and the front end will know to refresh if it doesn't line up with the backend. The backend will tell it to refresh. Let's talk about security. Since at compile time, this is baked into your backend. It is basically the same as if you had coded it in any other framework into your backend directly. So GraphQL, for example, has a problem in practice where you've made everything so dynamic and configurable, and the client is in charge of asking for things from the backend, and like you find yourself wide open. The client can ask for anything, and the backend will just serve it. That's not the case here. This is baked, and it is fixed. It is static. The data accesses will be exactly what the developer determined at compile time. So you have a security model that is basically equivalent to that of REST. I'll talk about DAG bytecode later. All right. Next, I'm going to show you the chat app. Now, hopefully you've seen this already. If you haven't, the first thing to note is it's multiplayer. So they are talking to each other. How can that work? The way that works is here we are defining an atom, a poor man's database, and that atom is not defined in Electric, but is defined in Clojure. Any connected client, if you have multiple tabs, each tab will connect to the Electric server. The server is all on one machine. The server has shared memory. So this atom is available in shared memory as global state because we defined it globally using def to all connected clients. So what happens here is we watch the atom. And what watch does is it's a way to convert a reference type that can be sampled like an atom into a reactive value. This is like the bridge. And each connected client gets its own watch, but all the watches are registered to the same atom. So when the atom changes, it will broadcast to all clients through the DAG because they're all registered to the same atom. So that's how multiplayer works. If you wanted it to be like more than one server, then you need a database. You can have your like a database, which is essentially global state that is more global than a global in your server. Would rendering still be optional if we use React components via reagent interop? You can, first of all, you can use React with Electric. We have an example of how to embed React inside of an Electric component. But this question is about optimal re-rendering, and React does not have what's called fine-grained effects. React has this ad hoc composition model where if something changes, the whole component will re-render. That is different than the functional effects system rendering, where we compile, even like inside the code, we compile everything to a DAG, and each S expression is individually reactive. So you get pinpoint precision rendering, like the best possible optimal rendering falls out of this DAG. So it would be more optimal to use Electric. And to be clear, there are other alternatives to React in the JavaScript ecosystem, which do promise fine-grained rendering. Hope I answered the question. All right. What else can we learn about the chat app? Let's talk about latency. One thing you note is when you type this, there's a propagation delay as you cross over network, and then it streams back to the other side. So if you look really closely, it blinks yellow when I type. Hopefully you can see that through the screen share. What's happening is here. When you press enter, and when the string you type does not blank, transfer to the server, and run this effect, swap the global state on the server, and V is used in lexical scope here. The compiler, of course, knows that this V here inside of this sharp lambda is actually a stream, and it knows to stream it from the server. It takes the stream from here and it renders to the server. And then this, because it's on the server, we don't yet know the result of this swap. We don't know if it succeeded. We don't know if it failed. We don't know if like the network connection dropped. So what we do is we will throw a pending exception right here. And the pending exception works like an exception. It will bubble up the stack. Here's the try. Here's the catch pending. And we will run this side effect by adding this resource to the DOM by attaching a style node to the DOM and then setting the attributes on the style node to be the topmost div. So what div are we inside? We're not inside the UL. We're actually inside of the div outside of this function. It might even be the document body. At some point, the exception will go away because the result is known. At that point, the pending exception is gone, and this will be canceled. You recall earlier we talked about functional effects systems give you this ability to cancel a resource and clean it up. This will be canceled. The body, the catch block is canceled. The DOM style node's cleanup callback will be called, and this will be removed from the DOM. How is set execute if swap throws an exception? So that's a great question. In this example, these two things happen in parallel. There's an implicit do here, and the implicit do will run both of these. It will run this, and then it will run this from left to right, but they will run concurrently. So this will happen. This message will be sent to the server, and then this will be set optimistically. This effect runs optimistically. So you immediately see that you see a problem of how do you roll back this side effect if this failed? And we did not do this in this demo. We are working on a library called Electric UI. We are on our 5th iteration of this internally. And the purpose of this library is to provide a graceful and functional abstraction that can abstract over the idea of optimistic updates and pending, so that you don't have to roll this back yourself. So that is a problem that we have not released that yet. You can expect that later this year. In the meantime, we are making an assumption that this will succeed. Is electric backend stateful? Is a running thread session for each connected client? The backend is stateful. When a client connects, it hits a server which has a ring middleware, which has a WebSocket adapter, a WebSocket middleware, and the WebSocket is attached to the WebSocket is the object will remain alive until like the connection terminates, at which point the WebSocket will clean up. And attached to the WebSocket is the server half of this program. It is asynchronous. It is run by Missionary. So Missionary will manage the execution of this reactive program. Missionary is asynchronous, so you do not need multiple threads for this. Is it stateful? Yes, it is stateful because the front end and back end act as a sports team, so they need to understand like what play they're running, which page the user is looking at, all the way down to like is this callback running or not? The electric wire protocol will synchronize this state, and then thus the server knows that this callback is running. So yes, it is stateful. Okay, will swap return a value eventually instead of exception? Yes, it will return whatever the return value of a swap is, which will serialize and be sent to the client and then ignored. Obviously, that is wasteful. We can optimize it. We can analyze and understand, hey, there's an implicit do here, and the only value that's actually looked at is the last one. So there are lots of room for optimizations. We haven't done them yet. To date, we've focused on correct program semantics, not performance. Though to be clear, the performance is excellent. We've like you can even see when I type into this, as a consultant late in my career, I've made like a dozen CRUD apps, and I/O is really hard. Concurrency is hard. Electric already is better than anything I ever coded by hand in terms of performance, even without any optimizations. It's also out of the box, correct error handling, out of the box, no exceptions will be lost, out of the box, guaranteed resource cleanup. It provides a number of strong guarantees through functional programming that your average application that is hand coded simply does not have. It's just filled with bugs. So optimizations will come. All right, pending auth. How does auth work? Let's quickly go into the extended chat demo. This is the same demo as you just saw before, except with some extra stuff. If you go to this URL, you can actually chat with me if you are in the East Coast, because it's running on an edge network in the East Coast. So how does that work? Well, I set a cookie. The cookie is bound in scope when the server portion of the client boots. So here we can see the HTTP request that originated the WebSocket connection and then was upgraded into a WebSocket. That is bound in scope and retained. So you can get the username that I typed into the basic auth. And there it is, Dustin. So you have access to the session. Now is a good time to note the full Clojure and ClojureScript interop, which is very important. So this get in is not, it's not electric get in, it's Clojure.core get in, and it works. This is a Clojure dynamic. This is like Clojure code. If not, I believe that's a Clojure core macro. By designing electric in a way that provides a very high degree of compatibility with Clojure, we say 99%. It means that code that was written for Clojure without electric in mind is still good, especially pre-existing macros. So if not, thread macros, all that stuff still works. We even tested core match about 2 weeks ago, and core match works almost entirely, except it found a compiler bug in electric, or an analyzer bug that we'll fix. So we even have core match. So that's very powerful. It means you're not limited. It means when you want to build applications with this, you're not using like a new programming language. You're actually using like a mature, established, 20-year-old programming language, which is Clojure. It's got all this scaled up enterprise infrastructure, and you get all that when you use electric Clojure. Okay. And then optimistic updates. So we think we have that figured out. It's not visible here. Next demo. So this is to do MVC. Feed baby, buy milk. Oops. It is, of course, multiplayer. This works. Yep. So these are in sync. It's also full stack. So when you look at the to do MVC baseline and any other, ecosystem, it's a front end baseline. It's meant to demonstrate that you can build a real front end app with your styles. In Electric, all you need to do is add the eClient and eServer markers. So essentially, full stack application is free. You take the to do MVC program that was client only, and you add eServer around the queries that you want to be called on the server, and that's it. There are 0 line of code changes in addition to marking with the macro what you want to be on the server. So that's really powerful. Let's talk about the rapid data entry problem. Applications like iMessage, oops, here's my wife. Oh, I don't want to text her. I actually want to text myself. Here we go. Often we text really quickly. And as you can see, the text messages went through one at a time. When I sent these text messages, they were optimistically rendered into this collection view. And then the effect of sending the text message, which has latency and can fail, and it goes over the SMS network, each of these text messages progressed in isolation independent of each other concurrently. And if one of them had failed, the rest of the text messages would still go through and you would see a retry button on the one that failed. Now, CRUD apps today don't work like that. In your average CRUD app today, what will happen is when you type something, it will disable the input and make you wait until the request succeeds or fails, at which point it will allow you to proceed. And that's bad because it means I can't type fast. Like I want to send text messages fast. I don't want to send a text message and then wait for the promise to complete and then right. That's ridiculous. So this is another way to think of the optimistic update problem that we saw in the chat demo of how do you have a series of effects that progress to completion in isolation and concurrently and manage the optimistic maintenance of a list view while the items go through these progressive states. This is, you know, the same as the optimistic update problem. This is something that we thought a lot about in the last few months, and we think we've cracked. So the UI hyperfiddle, or sorry, the electric UI5 library, which isn't out yet, we're using to-do MVC as like the baseline demo. How do you build a to-do MVC that will never disable the input and never artificially slow down the user as they type, and also never lose error messages and allow it to retry in the right place and see the progression. And all of this should be done in a way that is a robust and rigorous abstraction, and the user should not have to think about it. If you had that, you could then essentially build Google Sheets, because the thing that sets Google Sheets apart from like other low-code tools, it has this rapid data entry. You can type rows in Google Sheets really fast. So this is an example of electric Clojure pushing out the frontier of what is possible, because you compare this to the other ways we make applications. They do not contain a sharp enough understanding of concurrency in order to formulate and express the problem statement of running these effects to progression in isolation. So when you take a approach to UI that is based on concurrency and functional effects, it gives you the language you need to think about this. And we're really excited about that. All right, I don't see any questions about to-do MVC. And how are we doing for time? 1:30, it's been about 50 minutes, okay. All right, let's look at the directory explorer. I'm not gonna show you the source code to this, it's just a demo. What we do here is we have a virtual scroll over node modules. And to be clear, Electric does not depend on anything from NPM. It's pure Clojure script. We just put in node modules here because it's like got 5,000 freaking items in it. It's the biggest thing we could think of. And so what's happening here is as I drag this scroll down, streaming between the client and the server are hundreds, thousands of records being streamed differentially through the DOM as I scroll in real time. And all of this is network transparent. This is just a for loop over a sliding window of width 20 for the 20 rows in electric Clojure. So this to me is an example of something that is really freaking hard to do with React and requires configuring data loaders. And even if you configure all the data loaders, it's still not as good because the compiler can do a better job of optimizing and diffing the network traffic than a programmer would ever think to do. Okay, questions. The programmer does not need to think about CRDTs him or herself, but the electric model language gives the tools to do that for them. Yeah, so let me sharpen that a bit. What it's not a CRDT. It's just a streaming DAG. It's just streaming messages from client to server. We're not replicating in a conflict-free way two values like a CRDT would do. We are it's just a different model. If you wanted to use a CRDT with electric, you could do that because electric is just Clojure. So you would use a CRDT library from Clojure, and write the Clojure code and embed that inside of electric because they're compatible. But the electric model language gives you the tool. Yeah, the electric gives you the tools you need to make programs that distribute across the client and server without needing to really think about that at all, other than to mark the points that are on the client to server. Let me show you another demo. This is the electric datomic browser. This is a video. So what we have here, it's just, I'll make it even bigger. So same thing, except it's over the Datomic API, like it's very smooth. And now that I've shown you that, I want to talk about like what the rendering looks like for that Datomic browser. If you look at okay, this is unfortunate. The screenshot I want the pixels I want you to look at are this TX instant right here, and it's grayed out by the video. But there's a TX instant column which shows like it renders the time. Okay, I want to now. So here's the time rendering column. Here's the electric cell renderer for this column. This is what the experience is like to write electric Clojure. You have a struct that came out of Datomic, right? Some Datomic type. That's M. M is some backend Clojure record. And you have the attribute in the grid that you're rendering, right? This is a column renderer. The attribute is TX instant. We dispatch on the attribute to say, oh no, it's not the right piece of code. I want it to line up. The Explorer might be the right one. Yeah, it's this one. It's the modify column. There we go. So you have the attribute is modified. Here it is, fs modified. We're now rendering this point. And you don't know if you want to render this string using the client-side date rendering tools or the server-side date rendering tools. It depends. Do you want it to render in the browser locale, or do you want it to render in like the application locale, right? How do you do that? And that's an arbitrary choice in electric Clojure. All you have to do is write eClient or eServer, and you can just switch arbitrarily between them. It just doesn't matter. It doesn't matter how deep your call stack is. It doesn't matter if you're using higher order functions or lambdas or whatever. The compiler will analyze your program, and it will split apart the DAG, and it will color it, and it will give you the exact thing that would have taken you like weeks to write as a REST app. It will give you the exact like correct structs to send over the wire to batch it properly. So you just don't care anymore. It's very freeing. Okay. Somewhat related to CRDTs, if supported, can you say more about regarding offline mode local first? Okay, we don't have that now. Right now, we are very much for connected applications like enterprise applications at work. That said, when I was talking about the optimistic update problem as seen in the iMessage and in Kudu MVC, and how you need to like optimistically maintain a collection while the effect progresses to completion, and then like retry, render the status accordingly. This is very close. This optimistic update problem is very close to the offline first problem. So we have a strong intuition that we are on the path to solving offline first in a rigorous way. That said, it is very much not a goal, at least not this year. It may become a goal 1 or 2 years from now. Optimistic updates is an explicit goal. I just don't want to promise that we're going to give offline support when that's not what we're trying to do. What we're trying to do is solve the rapid data entry and optimistic update problem. Okay. Y Combinator. I published this blog post yesterday. The point of this blog post is to talk about what strong composition means. If you look at React server components, they also have some form of a component model that can embed a client component inside of a server component in such a way that you get what feels like a nice and declarative programming model. So we wanted to explain the difference between this and React server components. And the difference is Lambda. We have built network transparency into Lambda itself. So what that means is the compiler will analyze all the lambdas and instrument the lambdas such that the lambdas transmit, their streaming environments to the client or to the server based on their runtime execution state. And this is implied. All of this network traffic is implied by the shape of the AST that you programmed. And because it's actually Lambda, it means it doesn't matter how complex your compositions are as long as they're Lambda. And the Y Combinator is the hardest example I could think of. How can you have a Y Combinator to walk over a computation that is both on the client and the server? So first, what we have here is we are rendering factorial. I apologize for the typo. We switched it at one point and forgot to update it. But this is a factorial coded into recursive style here. That is also rendering to the DOM as it goes. We're rendering to the DOM by point effect managed by the effect system. And here's the recursion, and it's written in the normal recursive style you're used to, except it doesn't call the function itself, and we haven't named it. We're using the Y Combinator to inject the recur continuation, so it's called like this. And the point is, this is this. You just need to drink a lot of coffee and stare at this for like 4 hours, and you can kind of piece together how it works. But this is a very intricate call stack, so to speak, happening here. And Electric doesn't care. Electric Lambda just understands the reactive frames and transmits them accordingly, or manages the effects accordingly. So what you get here is a file system on the server, and we are rendering it, walking that file system on the server, and then rendering it to the DOM, and just switching to the DOM using eClient so that you don't need a second pass. It's all in the same recursion pass. And if you type into it, it updates. There's the markdown file. So it's a reactive recursion, and the reactive recursion is streaming across network. So here it is. Here's your interop. Here's Y. Here is the recursive visitor. Here is the Clojure Java IO file. So this is a Java IO file types that we're using. We're using Java. Here we enter the recursion, and H is a Java file handle, and we check if it's a directory, and that's on the server because is directories on the server. It's even that function exists only on the server. The reason it's wrapped here is because we just realized we hadn't implemented the dot special form yet for Java interop. So we don't have Java interop here. We only have JavaScript interop. So you have to wrap it. So we'll fix that shortly. There's an oversight. So here we are on the server, and then you switch to the client right in the middle of an if, right in the middle. And you render the LI, and what do I render in the LI? I need to get the file name, switch back to the server. And it's just completely arbitrary. You don't need to think about any planning or coordination or whatever. It just works. And then here's recursion. We're doing a recursion right in the middle of a for loop. which is interesting because like as I type into, I'm going to put an inline style on this to show you the life cycle of the actual DOM node as this recursion reflows. So background color red. There we go. And if I type y fib, you can see that the DOM was left in place. It was reused, despite the fact that there's a Y Combinator trampolining the recursion, and there's just this crazy reactive like frames happening. It's efficiently managing the DOM straight through all that, and it is also efficiently managing the network. And this stable use of and very intentional use of DOM allocation, this isn't written in the DOM layer. This is inherent in the evaluation model and semantics of the language itself of electric Clojure. So if you want to write a DOM renderer, it was 300 lines of code. It's like the simplest thing ever. It's just point effects and macros to get you the declarative syntax. And you may have seen recently a user contributed a 3D renderer for 3.js bindings for electric, and it was similarly something like 300 lines of code. It was his first electric project, and he did it in 30 hours. You know, his first project. So that's how powerful it is to have a general purpose reactive rendering managed by a functional effects system. Okay. All right, let's talk about functional core imperative shell. A theme that I want to revisit is the idea of what is essential and accidental complexity. I propose to you that this recursive traversal here is essential. There is not a single line of this function dir tree that can be removed without changing it. So we propose to you that this is the essence of a tree recursion and rendering it to the DOM, and there is no boilerplate here. At the same time, it is effectful as well. Like when we talk about functional programming, we're used to thinking of like, well, that means we want to program with values, and we want to make as much of our program as possible deal only in the domain of values and keep all the imperative framework code to the edges of the system. And React.js itself is an example of this. We represent the virtual DOM as a data structure, and then we have a reconciler to like, given this command, this description of what the DOM should look like, it should make it so. That's not what's happening here. This rendering is effectful. We are rendering by side effect. There is no imperative shell here. What we are actually doing is orchestrating rich fabrics of thousands of effects seamlessly by building them into Lambda. So we are no longer scared of side effects when we program with electric Clojure, because the functional effects system promises to manage them for us correctly and promises to make sure that the cleanup will always happen when the computation ends. So functional core imperative shell, we believe, is a mistake. We do not want to avoid using effects in our programs. What we want is to learn how to tame them, and having tamed them, we can now scale up and orchestrate them to a level that we could not have conceived of without an effect system. Finally, what can you make with Lambda? Okay, so given this magic Lambda with magic network, what can you make? I mean, Emacs, database, all of these things, like cloud infrastructure, you can imagine instead of eClient and eServer, you can imagine having more sites, eClient, eServer, eService1, eService2, or even building like a serverless platform, serverless infrastructure itself, where you can distribute different regions of a Lambda across your cloud infrastructure. This abstraction could let you do that. So to loop back to like the goal was, let me put it back on the screen. I don't have it written down. The goal is to raise the abstraction ceiling in web development and allow us to build richer applications that we can't express today. And Lambda is the way you do that. Lambda is the way you build abstractions that don't leak. Lambda is the way that you don't need to ruin the essence of your beautiful code, your perfect recursion, and interleave it with framework boilerplate. Lambda is the answer to that. Okay. All right, we're nearing the end. Let's talk about Tutor MVC Composed. What we've done here is we've taken Tutor MVC and put it inside of a for loop like this. So this is a demonstration of composition. The claim is that electric Lambda can build into Lambda rendering, computation, network, DOM effects. All of these things can be packed into a function. And thus you have a application primitive, which is a function. The application is a function. So what you have is a application function that composes like functions compose, and that means you can put it in a for loop and scale this. You just have an application and you compose it with your for loop. That's all there is to it, right? You can see it's the same function because I've their state is synced. So now we can go back to our problem statement, like Facebook has composable views and they have state network interaction rendering. How do you do that, right? It's not GraphQL, it's not ORMs, it's this. This is the unit of composition. We've built a Lambda that can express this. Okay. What does it mean? This is a demo of part of why we built Electric. We started with this gender shirt size example where we say, here is a function, it expresses the composition we want that any beginner programmer can understand, but it doesn't work because it's distributed over the client server system. And we now have what we need to fix that. It's an electric function. This is an electric for, and you need a server. Run the queries, run the server. I actually don't want to modify this, so I'm going to stop. Given this, can we now abstract higher? Because anyone could write a macro that like a declarative forms DSL that compiles to this. And that is what we are attempting to do with HFQL. So what HFQL is, I don't want to show all of this quite yet, is called Hyperfiddle Query Language. And this is a Eden-based DSL right here that simply macro expands to something that looks like this. And given Electric, I think anyone could write this macro expansion. It's not even hard. The trick is, right, how do you make this into an application, right? We have an Eden-based query, and it calls a function, and it queries the database, and it renders it as a data structure. But how do you render it as a form? So what we do here is we just swap out the renderer with a different renderer, with an effectful renderer. It's the exact same HFQL expression, except this time it renders as an application. It uses Clojure specs on this datomic query or this DataScript query to understand that this here, this unfilled parameter, is actually a string, and the string is called needle in the spec, and to prompt here an input to collect the filter, so that when I type in this filter, it filters the database. It will produce a topology that looks like this, and it will. You need a filter state, and then you need some sort of atom. Let x equal atom whatever, and then we say this is the atom. We need to say the reference reactive is derived from the atom. So we do this. And then we say orders is dependent on X, and that's all there is to it. We now, when we type into this atom, it'll rerun the query on the server. I unfortunately can't demo it because I didn't finish wiring this example together for you today. So you'll have to trust me. So then the question is, well, what does this scale to? And I take you back to the example I showed you at the beginning of the talk. How could we make a low-code tool that lets you type an Eden-based DSL and gives you a live application out the other end as you type? And since it compiles down to Lambda, it has no limitations. It can do anything that Lambda can do, including have arbitrary widgets, select options. You see here, I'm going to fast forward a bit here. You see here, there's an options query, which calls a backend function, which depends right here. It's side referencing to this gender value from the record and prompting for something on the client. So you get like server pagination. All like the DSL can do all of this. And since Electric is taking care of the network sync, it's actually easy to write this. This DSL is, I think it's 800 lines of code. And it scales to much richer applications than that. Let me go, here's the current state of it. So this is built with this DSL. And it is a operational CRUD app that meets the operational requirements of a Series B startup with 10,000 users, 20 pages, dozens of transactions. So this is what we mean by abstract higher with Lambda. And this is also how we measure our success. Like part of how we got to Electric was the thing that came before Electric was just not good enough. It was just yet another heavy abstraction over I/O, and it couldn't do this well. It couldn't do it well enough. So we stopped and we thought harder, and we worked with the best researchers we could find, and this is where we ended up. Okay, I'll stop here for questions. We can also talk about entry point and deployment, project maturity. Well, let's talk about product maturity first. So we have 2 design partners, funded startups. So this is ready now, this is used by them. Consumer-facing apps. If you're ambitious, we have some like minor rendering artifacts that will be resolved. Soon. Right? This is the use case we are intended for. We do internal production support apps today because the requirements are less stringent. Right? If there is a glitch in the rendering, it's not that big a deal while we iron out the bugs. Of course, before productivity tools, I wouldn't use it for that yet, but we're getting there. Dozens of HASI projects, and then maturity-wise, you expect the usual issues. So error messages are not perfect, though we do have async stack frames, the same way React.js has a synthetic stack frame. We have our async stack frames will reconstruct the client server interleaved stack trace that shows you the transfer points. So it gives you the stack trace that you would want to see, not the the reactive crash. And can you use it? We think so, yes. We dogfooded it for 2 years because like we understand as consultants ourselves, like what you can and cannot put into production. If you try to use Electric and like the if statements were glitchy because like there was some bug in the reactive engine or the network engine and your app got out of sync, right? You close the tab and you never try it again for 2 years. Like we understand that. It just can't happen. So that's why we waited so long to release. We've been working on this since 2021 or 2020 really. We released in 2022 last year to our friends, family, and customers, and then we released publicly 6 months ago. Do you have capacity for additional custom implementations? Yes, we do. We are adding 1 more in the next month or 2, and probably not more than that because we do need to focus. We're here to deliver this technology. We are not trying to make money right now. What are the realistic latency requirements for applications to work well? The first thing we did when we got this live was we tested this application over node modules, this virtual scroll over node modules, hosted in Paris, and across the Atlantic Ocean, I would use it in Philadelphia. And it was well within acceptable latency, especially compared to like your like Notion or your average SaaS app, which just is like, it falls apart. It's slow, glitchy, crashes. So we think it is already better, substantially better than the status quo, just because humans shouldn't be coding I/O by hand. It's a concurrency problem, right? We are not good at that. It requires deep mastery to write concurrency code. At the same time, our example apps are deployed to an edge network. We use fly.io. We do this because our demos are like accessed by people around the world. So we deploy in 5 different edge networks across the world, and you will route to the one that's closest to you. So if your application can be deployed to an edge network, you're going to see like 10 millisecond latency, which 10 millisecond latency is so good that the problem I complained about rapid data entry and back pressure, you actually can't even see that problem because like the transaction is accepted so quickly. Of course, if you have a central database, I don't know, you have to pay the cost from fly to US East, which is like another 2 milliseconds, and then your database may add 10 or 20 milliseconds of latency on that transaction. So you're looking at like, I don't know, 60 milliseconds for a round trip. It's still like, that's like a video game. So I don't think latency is a problem. We don't claim to have perfect network. In fact, we claim to have a very non-ideal network that is not optimized at all. And nonetheless, despite the fact that we have spent 0 time optimizing the network, it's still better than the status quo. But now, having framed this as a compiler optimization problem, right, there's a clear path forward to like applying graph theory, applying compiler theory to optimizing the network. So we look forward to understanding how fast we can really go. Okay, issues. The number one issue is slow builds. Like if you clone our starter app, the builds are like, a couple hundred milliseconds as you're expected. But as you get like, 3, 4, 5,000 lines of electric code, you'll experience 20-second compile times, maybe 30-second compile times. And we do not have incremental builds yet. So you pay that on every file save, on every incremental build. We are fixing this. The reason we allowed that to not be fixed for so long is simply because we are focused on correctness and language semantics first. It is now time, so we are going to deal with that. No hiccup yet. This is probably our number 2 most requested thing because right, you have this fairly verbose syntax, which is if you're doing markup like as a front end designer and trying to have a styled app with Tailwind, it's not awesome. There is a reason we haven't landed hiccup yet. We actually had it. We've tried it twice. Electric is more expressive and has a more powerful component model than Reagent does, and the hiccup has edge cases which damage the electric composition model. It has like ambiguities. So we hesitate to commit to a syntax when we don't even understand like the requirements that such a syntax needs to have. So we apologize. Some hiccup or rather something like hiccup will come, but doesn't look like that will happen this year. Stream your rendering, what that means is if you have a big app, sometimes you can see like the app stream in. Like if you rip this down fast enough, you can see the elements stream in. So another way to say this is the rendering is not transactional. The rendering is optimistic. We render as soon as we can. And if the query is slow or there's latency, you can see that. So we'll probably address this, or we'll work with our customers to understand like the actual production real world usage and make sure that like we do the thing that a real application needs, not just like slow down the app and make it transactional because it seems right. So we're being careful here. Do you think you could describe the recent improvements to missionary? Sure. Ask me again at the end of the talk, which we're shortly reaching. Loss of state and disconnect. What this means is if the server deploys or if your connection is lost, like you blur the tab and then the WebSocket times out and then you come back, it will reboot and you will lose your state. So on deploy, it will reboot and you will lose your state. We can fix that. We actually tried to fix that 6 months ago because of this deploy issue of the refresh and deploy. We didn't want to have to suffer a refresh on deploy. So we POC'd it and we realized that we had a problem in the electric implementation that needed to be fixed. So we've actually been rewriting and improving and refactoring the electric runtime based on all these learnings from being in production with hobbyists and with our customers. So when those changes land, we can revisit the loss of state on disconnect. We've already POC'd how to resync on connect. What are your thoughts on other Clojure front ends using Clojure Dart? We can absolutely use Clojure Dart. I see no reason that wouldn't work. Obviously, it's not a priority. We would need a customer to sponsor that. Can you compose client-side components? I'm not sure what you mean by compose client-side components. If what you mean is well, you kind of are. Like if you mean like call an electric function within an electric function, sure, absolutely. The electric composition model, electric lambda, you don't need to use the server. You can be client only, and if it's client only, you don't even have to write eClient. You just write it once at the entry point. So it composes the way functions compose. So I think the answer is yes. Okay, and of course, we are committed to this. A problem with many really cool projects, like past attempts to do something like this, is it's hard to make money and you can't afford to like bootstrap any longer and you have to go get a job. That's already happened to us actually, and we survived it. We have a stable business. We raised some venture capital and we're not dependent on the venture capital. We're currently financed by customer implementations. This will be here for a long time. Even if somehow the worst should happen and we run out of money, I am committed to this. For 10 years, I'll figure out a way. And I think much of the team is too.